Hello and welcome to Particle Tutorial 3. So in this tutorial we're going to be looking at how to control particles like a flock of birds to be able to attach meshes to them and have the animation, the cached animation of the meshes being driven by the speed of the particles, or basically how far they've traveled since the start. So this might seem a little simple, but it uses some really cool techniques, and I've used this kind of technique lots of times over many years, over many jobs, to animate meshes by using particle motion. So as I said, I've done all sorts of different versions of this for different jobs over the years. I've done flying books, I've done birds, I've done bees. I've even done one with flying laptops, and I've also used this technique to control animated meshes of people moving around on the ground, and other weird things like this one here. So this was the first one I did as a test when I was writing the first version of the 3ds Max script that I was developing to do this kind of thing. So I was using particles to put particles on a surface to keep them apart and to search a goal and to keep them on the ground, and then I attached animated meshes that figured out how far things had actually gone on each frame to be able to drive the cached out particle animation, or the mesh animation, to drive so that they were pretty much sticking on the ground. This was a work in progress, so the particles were a little bit jittery. So it was fairly early, and this was like a viewport preview with depth of field turned on. It's like a Play Blast or a flipbook. So let's start here, and I'll just save this one. Save, and I will new and save your scene as I'm going to save it as Flock of Seagulls vid. Recording the video with it. So always save your files before you start, so that when you're pathing things, it knows where the $hip variable is, because the $hip variable it defines the directory where the hip file is stored, and you use that to path everything in Houdini, especially with your assignments, so that when I load up your scene, if you've got any external assets, they will all load in properly. So to do this tutorial, you will need an animated mesh of something like a bird or a fish. I've supplied one of a seagull that I animated a few years ago that you can download to use for this tutorial. I'll supply that link under the videos. Or you can make a basic something yourself by making some objects and animating them and caching it out. So even if you make a shape to make some butterfly wings, and then you animate a butterfly and cache that out, you'd be able to use that for this as well, or a fish swimming as well. So make sure you put the cached animation folder in the same place that you just saved your hip file. Otherwise it's going to be hard to path things with the $hip. So the first thing that we're going to do is create a GeoNode, as always. GeoNode, drop it down and dive in. Actually we'll name that Flocking Gulls, and dive in. Yep. So inside the GeoNode, add a file node, and we're going to import the cache animation with this. So drop down to file node, browse. Normally goes to hip, but it's a good idea to click on the hip variable over onto the left just to make sure, and then I'm going to go into the seagull bgeo.sc folder and browse and load that animation from there. So let's check the scale of the seagull. It looks a little bit big at the moment, so I'm going to add a transform node to scale it to 0.4. 0.4, there we go. So always check scales are about real world size. Remember that Houdini units are in meters, whereas Max and Maya are centimeters. So if you bring anything in from other 3D programs, make sure you are aware of what size it is coming into Houdini, like rigid body simulations, cloth simulations, anything that's physics based. You really want to try and make things the scale that they need to be, so the simulation looks right. Not as important for particles, but I would say that anything that you make in 3D, unless there's a specific reason that you shouldn't make it at real world scale, make it at real world scale, so that when you want to reuse it in a different scene, you're not having to try and convert scales. Cached stuff can be scaled easily, but if you've got rigs on things and you've got animated stuff and the rig wasn't actually made to be scaled, because you have to actually make rigs specifically to be scaled. If it's complex, you need to incorporate the ability to scale it within the rig. And if it's rigged like that and you try and scale it, more often than not, it won't actually work very well. So you might want to add a color node next. So color, I'm going to make mine black, so I end up with some nice silhouetted black against the blue sky type situation. So if I scrub the timeline, I'll zoom into the current seagull animation that I made. So if you scrub the timeline, you can see it's loading in and it gets to frame 19 and it starts erroring. So we need to tell the animation to loop to the start, back to the start after frame 19. So to do this, we can use a time warp. So add a time warp. Activate it, layout H, yeah, and set the input and output frame ranges to match the number of frames in the animated cache sequences, in the cache sequence. So if you remember, it was 19, so let's change the output and input frame range from 1 to 19. So basically it's saying what we want to do is, like, the input frame range, we're going to tell it that we want to use input frame range to 1 to 19, but we want to use the same output frame range. You can use this to just chop out sections of cached animation as well, but we want to change the input frame range to post cycle, so that we can get a loop on this, so that once it gets past frame 19, it will continue looping indefinitely. So if you needed to cycle the before the actual animation started, change the other drop down to pre-cycle as well here, but we don't need that, so I'll just leave it on pre-hold. So next, to make some particles to fly around the place so we can attach copies of this seagull to them. So I'm going to make the particles from a sphere, so I'll make a sphere here. I'm going to make sure it's polygons. So next I'm going to turn the sphere into a volume. Actually, it's torus written there, so I'm going to write a sphere. I'm going to turn the sphere into a volume. So in the past, I think I've used an ISO offset. I used to use that for the first week tutorial, but I think I've switched over to mostly just using VDB from polygons. So it's a newer way to do the same thing, and yeah, like I said, it's called VDB from polygons. So make one of them after the sphere, VDB from polygons. Great. Activate that. Now it's using a distance one at the moment, but we want to use a fog VDB, and let's have a look at the time warp to see. Hang on, let's have a look at that. Yeah, and then we'll have a look at the size of the sphere. Yeah, that's not too bad. So we've got a volume there, and we can't even see the seagull inside it there. So a lot of the newer ways to handle volume data, meaning this fog that we've created here, So volume data, a lot of the newer ways to handle it is with VDB operators, and VDB or OpenVDB is a library of functions to store and manipulate volume data, which was developed by DreamWorks. So OpenVDB was introduced to Houdini back in version 14, and a lot of the older volume functionality in Houdini has been superseded with the newer OpenVDB tools. So as I said, make a VDB from polygons and turn off distance VDB and turn on fog. And as I said, the result looks fine on this at the moment. So next we're going to do the same thing as we did in the first week, where we're going to scatter points through the volume as a starting point for our particles. So put a scatter node, scatter SOP, and change the force total count to 100. You can come back later and add more particles to add more seagulls, but for the moment 100 is a nice amount because it'll keep it relatively responsive. Next we want to add some normals to the scattered points, so we can use the normals as an initial direction and speed for the bird particles. So basically we've got all these birds in here and we want them to fly outwards from the center, just so that they're not sort of getting complicated and bumping into each other to start with. It's not a bad place to start. So to do this, we can transfer the normal attribute from the sphere that the birds are facing outwards from the middle. But if I turn on the show normals toggle with the sphere, yep, it's only showing that we've actually got some vertex normals. Or if we were looking here from the VDB, there's none here. So what I'm actually going to do is add a normal SOP in here. So the normals that we were seeing here are just sort of like the implicit normals that are calculated by the directions of the faces of the polygon. So if we look here on the sphere with the middle mouse, there is no normal attribute here. So when I go to normal here, you can see that there is normal vertex attribute that we can transfer. So next what we need to do is transfer the normals from here down onto the scatter, because if we look at the scatter, there are no normals on those points that we scattered. So we'll do a transfer, attribute transfer, or transfer attribute. What is it? Attribute transfer. So we're going to, so wire the scatter into the left and the normal into the right. So remember that you can hover your mouse over the inputs of nodes to see what it wants you or needs you to plug in. So let's have a look. So have a look at the attribute transfer. So we can't see any normals yet because we need to tell it which attributes we want to transfer. So we want to transfer point attributes, and we want to transfer n for normals. So it's still not actually working. So the reason we're not seeing the normals on the scattered points is that when we added the normals, we added them to vertices. So switch that to points, and you can see that the scattered points that we've got from our VDB from polygons is getting the normals attribute transferred onto it. So that's not a terrible starting point for directions and speeds of birds. So when I was back on here, remember that as I mentioned in previous tutorials, vertices are used on the corners of polygon primitives, and we don't have any polygon primitives on the scatter, so there are no vertices to transfer. So that's why we needed to change the normal to points, because we're actually transferring it to points. Okay, so now as I said, we can see the normals on the scattered points. Great. But although the normals are the right data, they're not named the right thing for the PopNet to understand, to be able to use for particle velocity. So what we're looking for is a small v attribute for velocity. So we'll add a wrangle, and we'll convert the v point attribute, the velocity, to a normal, we'll make the v point attribute from the normal point attribute. So make a wrangle in here, Make sure it's a point wrangle over here. So then we'll type in small v because we're making a vector, and a for an attribute, v for velocity, equals at n semicolon. So basically we're saying we want to make a velocity vector, and we want to make it out of the normals that we've transferred from the sphere. Let's have a look at the wrangle. Yep. So if we look on here on the attribute transfer, we have got the position and we've got the normals that we transferred in, and then when we go down to the attribute wrangle, we've also got the velocity here. If we look at the geometry spreadsheet, you can probably see, I'm assuming that they're going to be the same value, so normal x is the same as normal v. So we've basically converted the normals into velocities that we can use. So now we have the points as places to make particles from, along with the velocity attribute to show which way we want the particles to fly initially, and we can make a pop net after the wrangle. So as I've said, a pop net is just a dynamics operator network with the particle related stuff already put inside it. So to start with, there won't be any particles because we need to change a setting that defines what the particles are being emitted from. So on the pop source, the source tab, so on the pop source here, on the source tab, the emission type by default is set to scatter onto surfaces. Now we don't have any surfaces here, so it's not emitting any particles. We need to change this to all points, which is that one there. So now if I play through, actually I'll turn off the normals or the velocity, yep. So now we should be able to see a steady stream of particles coming out from each of the scattered points. But we only want one particle from each of the scattered points on frame 1 and then no more. So let's have a look at the birth tab on the pop source. So the pop source was still here, oh, not in there, so select pop source, then the birth tab. So impulse activation is on. So if we turn it to 0 and rewind and play again, you can see that it stops the particle emission. So impulse birth will emit from every point once each time the node cooks, which by default is once per frame. So if we leave it on 1 at frame 1 and then animate it to 0 on frame 2, that should give us 100 particles emitted from the points that we made at frame 1, and then no more from any subsequent frames. So I'll do that now. So impulse activation on frame 1, I want it to be 1, and then on frame 2, which I'm going to need to keyframe that. Sorry, I forgot to set a keyframe on the first frame. So remember, holding Alt and clicking on the value adds a keyframe, and it goes green. So I need to make sure that it's 1 on frame 1 and 0 on frame 2. So now let's have a look. Yep, that looks cool. So I'll explain one of the other options for this. You don't need to follow along because I'll just switch back to these settings when I'm done. So you can see the constant birth rate is actually grayed out at the moment because we have the all points set on the source tab. So if I switch to points in here, you can see when I go back out, there are now more options available for constant activation and birth. And these values relate to how many particles are emitted per second. So this is something that you might want to look at for other things, but this isn't what we want for this. So as I said, so I'll switch back to all points so that we emit from all points on frame 1 and then no other particles after that. So we can hook up, we can do a test to hook up the seagull animations to see how it's all working. So jump up into the geo node and make a copy stamp node and name it copy to particles. So it's called copy stamp. So I'm going to name it copy to particles. Great. So put the pop net into the right and the time warp of the seagull into the left. Let's have a look. Get rid of the geometry spreadsheet there for a moment. So this copy stamp, sorry, is similar to the standard copy to point stop, but it allows us to pass information in a more powerful way to the particles, from the particles to the meshes that are being copied to them. So let's scrub the timeline and see what's happening here. So we have seagull attached to each particle, and they're flying out in the direction that we initially got them to. Now I can tell that a lot of these are flying right next to each other, so it might actually pay for me to turn up the frequency of the sphere so I get some more rounding on the motion there, on the initial motion, so that it's more of a spherical thing rather than a faceted. So yeah, that looks a bit better. Cool, so we have seagulls attached to each particle. So that's a good start, but I'll end this video here. So in this video, we loaded a cached animation of a seagull flying, and then we looped it. And then we made some particles and used the sphere to assign initial velocities by converting the normals of the sphere to a velocity attribute. And lastly, we connected the animated seagull mesh to the particles. So in the next video, we will animate a sphere with a transform node and use the transform values from that to move a pop attract around the scene for the seagulls to fly towards. So it's a pop operator, particle operator in here that we can start trying to get the seagulls to fly towards that operator. And we will construct a motion path to see where our animation of the pop attract is going. To do that, we'll use a trail like we used to generate velocities on the character in the splash dance, and then we'll use a time shift SOP to only view the last frame of the trail of the motion. So it's basically like a animatable motion path in Maya, but this one's not animatable. It's just a guide to show you where the path of an animation is going. So, and then we will use a couple of other particle operators like pop flock to keep the particles apart, and pop speed limit to make sure they don't fly too fast. And I'll catch you in the next video.